Okay, what if I told you that the entire universe is just playing the odds? Today, we're going to dive into one of the absolute cornerstones of physics, thermodynamics, but we're going to look at it in a totally different way. Forget the complex science for a second. Think of it as the ultimate casino game. So, let's place our bets.
All right, let's kick things off with a little puzzle. Imagine you're rolling some dice, right? Just a random tumble. And then, over on your desk, you've got a hot cup of coffee that's slowly cooling down. These seem like two completely different worlds, don't they? But what if I told you they're both playing by the exact same rules?
Well, the connection is pretty wild. The entire science of heat and energy can basically be explained using the same kind of logic that gamblers figured out centuries ago just to win at dice. And when you really let that sink in, that simple idea, it changes everything. It kind of suggests that the universe itself is fundamentally all about probability.
So to really get how this works, our journey isn't going to start in some high-tech lab. Nope, we're heading back to the casinos of 16th century Italy. We're going to trace how the simple act of analyzing a dice roll somehow evolved into a powerful tool for understanding the entire cosmos.
You know, this idea didn't just pop up overnight. It built up over centuries. It all started with this guy, Cardano, literally just trying to beat the house at cards. Much later, a physicist named Gibbs takes that same statistical thinking and applies it to, countless tiny particles in a jas. But the real aha moment, the key insight, comes from Edwin Jaynes in the 1950s. He's the one who realized that thermodynamics is really two things at the same time. It's our best guess based on the information we have, but it's also about the actual physical laws that tell the dice, the atoms themselves, how to behave.
Okay, so how do we actually do it? How do we make that leap from gambling to a cup of coffee? Well, believe it or not, the entire theory rests on one incredibly simple, almost childlike instruction. You just have to count. That's it. Specifically, you count all the different ways that something can happen.
In physics, there's a term for these possibilities: accessible states. And here's the absolute foundational rule, and it's ripped straight from the gambler's handbook. Unless you have information that tells you otherwise, you have to assume that every single possible outcome is equally likely. Think about it, a coin flip, right? It's got an equal chance of landing heads or tails. That's the starting point. Let's make this super concrete with a simple dice roll. You can see here there are 36 different possible combinations when you roll two dice. But what we usually care about isn't the specific dice, it's the sum. Now, you can only get a sum of 2 in one way, right? You got to roll 2 once. But a sum of 7? Oh, there are a bunch of ways. A 1 and a 6, a 2 and a 5, and so on. Every single one of those specific rolls is an accessible state, and each one is just as likely as any other.
And the second you visualize this, the pattern just jumps right out at you. This chart here shows the number of ways you can get each possible sum. You see? There's only one way to get a 2 and only one way to get a 12. But just look at 7, right in the middle. There are 6 different ways to roll it. So because 7 has the most accessible states, it is by far the most likely outcome. This isn't magic, it's just simple math.
Okay, counting dice is one thing, but what about the trillions upon trillions of atoms in a gas? The number of possibilities it's just astronomical. You can't even write it down. So to handle these insane numbers, scientists use a concept called entropy. And really all entropy is a measure of our uncertainty, what we don't know. And they use a nifty mathematical tool, the logarithm, to shrink those gigantic numbers down to something we can actually work with. It's kind of like a Richter scale, but for possibilities. And you know what? This might actually sound familiar, because it is the exact language of computers. A single true or false question has 2 possibilities, and we call that amount of uncertainty 1 bit. So, an 8-question test, that has 256 possible answer sheets, but the uncertainty is just 8 bits, which you probably know as 1 byte. This fundamental unit of information, the bit, is directly physically tied to this whole idea of counting possibilities.
Okay, great. So we can count possibilities. But now for the really big question. What does nature do with this information? Well, just like a casino always wins in the long run, nature plays the long game. Physical systems will always naturally drift towards their most probable state. That's the one with the most possible ways of happening. And there's a name for that state: equilibrium. So here is the absolute core idea. When a hot system meets a cold one, think about your coffee in a cool room again, they start sharing energy. And they keep sharing it until they find the one single arrangement that has the most possible ways of existing. They settle right at the peak of their combined probability. And that's not just a good bet, folks. It's the only bet the universe ever makes. And we can actually see this play out mathematically. When you combine two systems, their total uncertainty, their total entropy, isn't just added together. Instead, it forms this very distinct peak. And that peak, that's the sweet spot. That is the most probable, most likely distribution of energy between them. It's important to remember nature doesn't actively look for this state. It just kind of falls into it because there are just so many more ways to be in that state than any other.
And here is the big payoff. We all know from experience that at equilibrium, the temperatures become equal, right? A hot thing and a cold thing become a warm thing. But why? It's because right at that peak of probability, a really key mathematical property emerges. The slope of the uncertainty graph becomes the exact same for both systems. And physicists looked at that and said, hey, let's define a new quantity based on that slope. And they called it temperature. So temperature isn't just some vague feeling of hot or cold. No, it's a precise measure of how much a system's uncertainty changes when you give it a little bit more energy. Two systems are at the same temperature when they basically have the same willingness to accept that new energy.
So, okay, this has been a really powerful way to think about physics. But can it actually make real predictions? I mean, can this gambling logic really give us one of the most famous equations in all of science? The answer is a huge, resounding yes. It's time to cash in our chips and derive the ideal gas law. Let's just walk through the logic step by step. First, we count the states. For a gas, the number of places its atoms can be is basically just related to its volume. Easy enough. Second, we find the uncertainty, the entropy, by taking the logarithm of that number. Third, we pull in a known physical relationship. How uncertainty changes with volume is defined in physics as pressure divided by temperature. Now for the fun part, step 4. We connect the dots. We take the math from our counting in step 2 and set it equal to the physics definition from step 3, and we just see what happens.
And boom, there it is. PV equals NKT, the ideal gas law. This isn't some random rule that scientists found after tons of messy experiments. Not at all. It is a direct, logical, mathematical consequence of simply counting possibilities. It turns out the laws of physics are, in a very real sense, just the laws of probability. Now, this information-based approach didn't just give us a new way to look at old physics, it literally ignited a revolution. It built a bridge between seemingly separate fields like thermodynamics, computer science, and even biology. And it completely changed how we see everything, from the data on our screens to life itself. I mean, the impact is just staggering. This way of thinking lays the foundation for so much of our modern world. How we compress files on our computers, how we secure our data with cryptography, how energy flows through entire ecosystems. It even gives us deep insights into the absolute physical limits of what computers can ever do. It really does touch nearly every aspect of modern science and technology.
So let's ask a question that gets right to the very heart of this connection. We live in a digital world, right? It's all built on bits of information. But does it actually cost anything, I mean in a physical sense, to create one of those bits? To flip a 0 to a 1 on your hard drive? Is there an energy price? And the answer is a definitive, absolute yes. This incredibly simple equation tells us the minimum cost. Every single time you want to create a little bit of order out of chaos, every time you record a single bit of information, you have to pay a tiny but completely unavoidable energy tax to the universe. Information is not free. Its currency is energy.
This line of thinking goes so deep, it even redefines our understanding of life itself. I love this quote from the source material because it suggests that we, as organisms, are really just temporary vessels. What's really evolving over the eons is the information, the genetic code. You could say that life is a kind of engine that uses energy to write and rewrite information, and that whole process is governed by the exact same laws of probability we've been talking about this whole time.
So, that brings us to our final puzzle. We started this whole journey with a simple bet, and we found that the logic of gambling seems to describe the entire cosmos. The universe apparently runs on information, on probability, on just counting the ways things can happen. Which leaves us with one last mind-bending question. If our universe is running some kind of grand calculation, what's the answer it's trying to find?